Hi Year 12. Today we're moving on to 5F and we're going to start looking and reviewing logarithmic functions. We first looked at these last year in Year 11 and it wasn't something that we were particularly strong at, so I think it's something that we definitely need to consider. This is not going to be in our second assessment task for the 2023 Year 12 class. If you're watching from another year, that may be in yours, but 2023 it won't be in our assessment too. So we first introduced log functions in Year 11. It was in Chapter 9. The function is the inverse of the exponential function. So in combining these together in a composite function, they cancel each other out. And the way that they cancel each other out is in these two examples below. So I have 2, and in the power of 2, in the exponential position, I have log 2 of x. Because I have a 2 here and a 2 here, these are basically cancelling each other out, and I'm left with an x. Likewise, if my log is my base and I have log 2 of 2 to the x, and that's taking the place of an exponential function, the log 2 of 2 is going to be 1, and I'm going to be left with just this x, which would have come down the front in our log rules and given us just x. I've just jumped over into our HSC formula sheet, and as you can see, that is actually given to us in the formula sheet. So you don't need to memorize that, and that's something that you might find that you do need to look at quite often. So log a of a to the x, the a and the a are cancelling each other out, and we're going to be left with an x. Likewise, if the log's in the exponential spot, this a and this a are basically cancelling each other out, and we're left with an x. That's basically what's happening with those. Okay, moving back to our notes. Now there was 2 types of logarithms that we had a look at in Year 10, logs that had a base e and logs that were base 10. The ones that we're primarily going to be looking at are going to be base e. And those logarithms of base e are important. They are natural, what we call natural logarithms. And given the prevalence of e in calculus and mathematics, logarithms of base e are called natural logs. And they're represented by this symbol ln. It is not in. I've heard people pronounce that as in before. It is ln, standing for natural logarithm. And on your calculator, that is primarily the button. I'll just jump over to my one here. You might have the Casio. That ln button there, that's our natural logarithm button, and you'll see that it's below our e to the x. So they're the ones that we're using on our calculator. We are not using these, and I don't want you to use this e at the bottom either, please. So we're using these ones. If you're on the Casio, it will be the same as well. Okay, so although we say that our natural logarithm is written ln of x, it can also be written as log e to the x. So e to the x and ln of x are exactly the same. I interchange between the two. Your books and your HSC exams may interchange between the two as well. Okay, so moving down a little bit, it's saying it is possible to switch between the different representations by applying the inverse function. So I'm going to start with this one here. If we've got y equals log e of x, how we write that as an exponential is this is our base. We have e to the power of y is equal to x. And you need to know how to change between this function and this one here. So e to the power of y is equal to x. If you remember that format, so the base to the answer gives us the x, then you can easily change your way around logarithms and exponentials fairly easy as well. Okay, so don't forget that your your base e has a value. So e to the power of 1 is about 2.718. So you can pop that on your calculator if you forget that number. So if you just pop in e, pop 1 in the power, gives you the value of e. So there's our value of e. So it does have a value. We generally like to keep our exponentials or our e as an e as opposed to writing it. Looking at the difference between the graphs, the exponential and log functions are drawn below. So here's our e to the x, which we've been working on, and it goes through 0, 1. Likewise, or similarly, our natural log graph, or y equals log x, goes through 1, 0. And these graphs are reflected about the line y equals x, if you have a look at that. And we have looked at that previously before. Okay, so there's some properties below of those graphs. And they're written below. Have a look at e to the x to start with. It's saying that the gradient at the y-intercept, so if we were to differentiate e to the x and sub in our value of 0, which we'd end up with, because we differentiate e to the x, we get e to the x. E to the 0 is 1, so the gradient at that point 1 would be 1. The domain of e to the x is all x. Our range is greater than y. It's 1 to 1, and we have an asymptote of being the x-axis. Y equals log of x. The gradient at the x-intercept, which is here, is also 1 because it's the same gradient as we would have on e to the x. Our domain is x greater than 1 because our asymptote becomes the y-axis. And when we differentiate log of x, we get 1 over x. We haven't done that yet. That's still to come. We'll do that in the next few lessons.